Have you ever really thought about what it means for something to be completely at rest? I mean, that final, settled state that everything in the universe, from a dying star to the coffee on your desk, is constantly, relentlessly pushing towards. Well, that final state has a name, and when you understand it, you start to unlock some of the deepest secrets of how everything works. So, let's dive in.
So let's just ask the big question right away. What is the final destination for everything in the universe? Think about when you pour cream into coffee. First, you get those beautiful, chaotic swirls. But if you just wait, it all just settles. It becomes this uniform, calm brown. That state of settling, that's what we're talking about.
And this ultimate stillness, we call it thermodynamic equilibrium. But here's the thing, it isn't really about inactivity. It's actually a state of perfect balance. And getting a handle on this idea is the key to understanding, well, almost everything, from how a car engine works to how a massive star manages to not tear itself apart.
Now, to really appreciate equilibrium, it helps to look at its total opposite. Just picture what happens when you dump baking soda into vinegar. You get that immediate, fizzing, bubbling chaos, right? It's intense, it's changing second by second, and it is a perfect example of a system that is very, very far from equilibrium.
It turns out, for any system to reach that true state of calm, that tranquility, it has to check 3 specific boxes. It has to satisfy 3 conditions all at the same time. You can think of them as the 3 pillars of balance.
First up is thermal equilibrium. This one's pretty simple. It means the temperature is the same everywhere. No hot spots, no cold spots. One single uniform temperature. Remember our fizzing beaker? That reaction actually gets cold, so it's constantly pulling in heat from the air around it. That temperature difference means it fails the first test. No thermal equilibrium here.
Second, a system needs to be in mechanical equilibrium. This means all the forces are perfectly balanced out and the pressure is uniform. Think back to all that bubbling and fizzing. Those bubbles are pockets of high-pressure gas rushing through the liquid. You've got turbulence, you've got movement, so it fails this test too. It is definitely not mechanically stable.
And the third and final pillar is chemical equilibrium. Now this is probably the most obvious failure in our little experiment. The vinegar and the baking soda are actively reacting with each other, right? They're changing from one thing into another. As long as that chemical reaction is chugging along, the system is, by definition, not in chemical equilibrium. And here's the absolutely crucial takeaway. This isn't a pick-and-choose situation. For a system to be in true thermodynamic equilibrium, it has to hit all 3 of these targets, thermal, mechanical, and chemical, simultaneously. It's an all-or-nothing deal. This is why engineers are obsessed with this concept, because if even one of those pillars is a little shaky, your entire system is unstable.
Okay, but wait. Does this mean that when something reaches equilibrium, everything just stops moving? Well, yes and no. From our big macroscopic point of view, yes. The pressure, the temperature, it all looks completely static. But if you could zoom in, down to the molecular level, you'd see absolute chaos. A frantic, unending dance of molecules bouncing around. The key is, for every molecule moving one way, another is moving the opposite way. The dance is perfectly, beautifully balanced.
So this state of perfect balance exists, but that just brings up an even deeper, more fundamental question. Why? Why do things naturally move towards this state? What is the driving force behind this universal tendency for everything to just settle down?
I mean, really think about that. This is one of the biggest questions in physics. Why does heat always flow from a hot object to a cold one, and never the other way around? Why does a gas always expand to fill a room? What is this invisible hand that seems to be guiding everything towards balance?
Well, the answer is a famous and often misunderstood concept called entropy, which is governed by the second law of thermodynamics. Now, you've probably heard it called disorder, but it's much more useful to think of it as just probability. The universe isn't trying to be messy, it's just that there are an astronomically huge number of ways for atoms to be arranged in an equilibrium state, and only a few ways for them to be in a very specific, ordered state. The system isn't choosing to be in equilibrium, it's just statistically doomed to end up there.
Here's another way to look at it, this time from an energy perspective. A system that's out of balance has available energy. It has the potential to make things happen, to do work. As that system moves towards equilibrium, it uses up that available energy. It's exactly like a ball rolling to the bottom of a valley. At the top, it has lots of potential energy. At the bottom, it's stable. It's reached its lowest possible energy state. That is equilibrium.
And I want to be clear, this is not just some abstract physics concept. These principles are running the show literally everywhere you look. Let's ground this with a few amazing real-world examples.
You ever look at a soap bubble? That perfect, shimmering sphere is a tiny arena of mechanical equilibrium, where the inward pull of surface tension is in a perfect standoff with the outward push of the air inside. Or what about a pH indicator changing color in a solution? That's a chemical equilibrium that you can literally see with your own eyes. Even the very basis of your thoughts, the electrical signals in your neurons, is possible because of a delicate ionic balance called a Donin equilibrium. It is everywhere.
Okay, so if everything in the universe is tending towards this final, balanced state, what about us? What about life itself? This is where the story takes a really fascinating and profound turn.
So here it is, the critical question. We've just laid out this universal law that seems to govern everything from galaxies to soap bubbles. So, does it also apply to a living, breathing person? Are you in equilibrium right now?
And the answer, in one simple word, is no. In fact, a living thing is profoundly, fundamentally, and I would argue, beautifully, out of equilibrium.
So, if we're not in equilibrium, what are we? Well, we exist in what physicists call a non-equilibrium steady state. It sounds like a mouthful, I know, but the idea is actually pretty simple. While some of our properties, like our body temperature, stay constant, that's the steady state part, we have to constantly burn energy and consume matter just to keep it that way.
The best way to picture the difference is with an analogy. Equilibrium is like a still pond. Everything is settled, it's calm, there's no flow. A non-equilibrium steady state, on the other hand, is like a fountain. The water level might look constant, but that's only because there's a continuous flow of water, of energy, pumping through it. A still pond is the state of a dead organism. The flowing fountain, that is the state of being alive.
This leads to a conclusion that is just profound. Life exists by constantly, actively fighting against the universe's natural tendency to settle down. We maintain our incredibly complex, ordered state by burning through energy. For a living thing, reaching true thermodynamic equilibrium with the environment, that isn't peace, it's death.
Which leaves us with this final thought. We've seen that equilibrium is the final destination for pretty much everything. It's the universe's ultimate state of rest. But maybe the most incredible thing in the entire cosmos is that life isn't about reaching that destination. Life is the journey. The incredible, energetic, beautiful journey of fighting to stay as far away from it for as long as we possibly can.